Hi, my name is Yush Kochru, and this is my lab for Physics 2212.5, Magnetic Braking with Faraday. The purpose of this lab was to collect observational data of a falling magnet through a conductive tube of aluminum foil, to model the magnet and tube interaction computationally, and to compare the predictions with the observed data. So our findings in this lab is that the computational time was 5.67 seconds, and the observed time was 0.68 seconds. The models and fundamental principles used in this lab are Faraday's law, Newton's second and third law, the Biot-Savart law, the magnetic force on a loop, and then change in magnetic flux with respect to time. So our assumptions in this lab is that air resistance is negligible. The only forces present on the magnet are the force due to gravity and the force from the loop, and that we can treat the bar magnet as a magnetic dipole. So the system in the initial conditions, the system in this lab was the falling bar magnet, the surroundings was the non-ferrous aluminum foil tube. Our initial conditions is that the magnet initially starts from rest, and that it initially starts at some position L above the aluminum tube. So the procedure for this lab, first use a magnetometer to find the north pole on the magnet, then measure the mass of the bar magnet, the length of the tube, the radius of the tube, and the width of the foil. After that, drop the magnet through the tube 5 times and record when the magnet enters and leaves the tube, and from there calculate the elapsed time of when the bar magnet traveled through the tube. So in the table, it shows the data from the 5 trials of dropping the magnet down the tube, and the average time from that was 0.68 seconds. The mass of the bar magnet, the length of the tube, the radius of the tube, the width of the foil, and the magnetic moment are also shown. In the glow script computer model, first the constants were initialized, the geometry of the tube was identified, and the numerical parameters of the simulation were also initialized. Then we created the tube, the aluminum tube, the bar magnet, and also the function to calculate the magnetic field of the bar magnet. Next, we calculated the gravitational force on the magnet along with the magnetic force from the tube. Then we used the function defined on the left-hand side to calculate the change in flux over time for the ring due to that magnet. And then after that, we were able to find the current that passes through the loop. Finally, we found the force of the ring on the magnet and the force of the magnet on the ring. After that, we were able to find the magnetic force of the magnet, and we added that to the gravitational force in order to get our net force. From there, we were able to update the velocity of the magnet and the position of a magnet, and then create a plot for this. And this is the graph generated in the glowscript code for the velocity versus time graph of the falling bar magnet. So the model comparison. When doing the experiment by hand of dropping the magnet through the tube, that average time over the 5 trials was 0.68 seconds. While using the glowscript model, I received a time of 5.67 seconds for the magnet to make it all the way through the aluminum tube. So the possible sources of error is that the radius, length, and width could have been measured incorrectly with the ruler. And the most likely source of error is that the magnetic moment calculated from lab 3 could have been incorrect, which would have impacted the glowscript model. So the conclusion. If the resistivity of the conductor were reduced as close as possible to 0, how would the dynamics of the falling magnet change? If the resistance was increased close to 0, then that means the induced current would be very large. Because of this, the force of the loop on the magnet would be a lot stronger, so the magnet would fall with slower speed and would take longer to actually travel through the loop. And if the holes or slots were cut into the tube, the ring's currents would be affected because the induced current would be smaller, meaning that the force acting on the magnet would also be smaller, and so the magnet would fall with a faster speed and take less time to actually travel through the tube.